Can I'm here.
So, Sasha, now it's 10, but we have a tradition to start 1-2 minutes later because
That's not a
Yes,
problem.
yes.
this will collect more people because they're as bad students come in at the very last moment.
Do you still see
Ochirov?
my title?
Yes,
Yeah, okay.
yes, everything
Sorry,
is
I'm
fine.
only showing one window.
Здравствуйте, Ира.
Yes, Хиро. Здрасте. Вот что с рукой-то у меня тут? Ручку сломала.
А что случилось?
Слам перелом.
А почему? Вы упали?
Упала, шла в институт и упала.
Ой-ой-ой. Ну еще нет гололедицы ведь?
Нет, прекрасная погода
Да.
на пустом месте.
Здоровья вам, здоровья.
Спасибо.
Здравствуйте.
Как-то производительность труда увеличилась, потому что теперь ходить некуда, бегать некуда, сижу-ка. Кстати,
Понятно.
шум.
Да. Ну а мы в Париже все.
Ага.
Сейчас в деревне.
В деревне? В деревне сейчас, да?
Да-да, значит, мы приехали на несколько дней. У нас сейчас гостит, между прочим, знакомая из Москвы.
Ага.
Через
Очень
Баку
рада.
прилетела.
Ага.
На неделю. У него тут литературный съезд.
Понятно.
Начнем?
Да. I think we can start.
Very good.
Okay, 30 people. Okay. Hello, everybody. Today we have a seminar by Alexander Ochirov. He will tell us about scattering amplitude for QCD, gravity, and massive particle. Please, 1 hour.
Yeah, thank you very much for inviting me to speak here. I was asked to give a kind of overview talk about scattering amplitudes. So I decided to give this talk that covers a bunch of topics at the same time, but hopefully it will be pedagogical enough, and it covers to some extent the content of these 4 papers, some of them written at ETH Zurich and Oxford, and the last one written already in Shanghai. But I really want to start with something really simple. Well, basically, this is the start of the scattering amplitudes topic as a research topic. The starting point is the famous Park-Taylor formula, which is a formula for n-gluon scattering. And just to remind you why it's so great, this one-term formula, let me remind you that that Feynman rules in QCD, they are not one-term. They're even a single 3-gluon Feynman rule is already, well, at least 3 terms if you count them generously. So, and then, of course, each such amplitude is composed of many diagrams. The amplitude has any number of particles, so it's a factorially growing number of diagrams, each of them constructed from this Feynman vertices. Each vertex has multiple terms. So normally, back in the day, people were not expecting things to resum into something nice. But the fact that it does basically gave birth to the field of scattering amplitudes. And this formula is really just a one-term formula for an infinite family of such amplitudes. And it's fixed by this acronym MHV, which basically translates to the number of minus and plus helicities for those gluons. So here I took gluon 1 and gluon 3 to be to have negative helicity, and every other gluon has positive helicity. And you can also read off the helicities from the right-hand side if if you've ever heard of spinning helicity spinners, of helicity spinners that are used in spinning helicity formalism. So it's a very transparent kind of formula. And it's just a one-term formula instead of a factorially growing number of terms. So this kind of simplification with respect to Feynman rules happens, well, we can now understand why it happens. One of the reasons why it happens is gauge invariance, that is very constraining in gauge theories. And the other one is the fact that spinning helicity variables that are used to write this formula, they are well tailored to represent the physics of this amplitude. So the physics at tree level of this amplitude almost boils down to the quantum numbers of the gluons, such as helicities, pluses and minus ones, as well as their factorization channels. And they are all visible in the denominator. So the spinning helicity variables just allow you to write this formula because they're well tailored to the answer. So in this talk, I want to talk more about massive particles. This is because for many people, it's still not entirely clear that our methods work very well for massive particles as well. In particular, I will talk about massive quarks to start with. And I will also concentrate on some tree-level methods in 4 dimensions, such as the one that can be used to derive this formula. Of course, there are loop methods available, and also you can use them in dimensional regularization to compute amplitudes at higher loops in DimReg. But for the sake of just this talk, we'll stick to tree level. So this slide just shows you a more recent family of results that I have obtained in 2018. So the first formula for is also a one-term formula. The term that's written in the numerator is slightly more involved than in the Park-Taylor formula, but overall, you see it's just one fraction. And all the poles are in the denominator. For this simple formula, it's also an endpoint amplitude that involves n minus 2 gluons, all with plus helicities. And then it also involves 2 massive quarks. And they have their spin labels, SU2 labels A and B. And you see that this formula is actually 4 amplitudes. It's a matrix 2 by 2. So it represents, in terms of helicities, it represents 4 amplitudes in one formula. And it's still one term. So this is you could in principle consider this formula to be a massive analog of the MHP formula when it comes to 2 quarks. And then you can also write massive analogs of next to MHP formula that tend to start to involve sums. And now this formula for when there's a one negative helicity gluon, it's not one term, but it's a linearly growing number of terms. So it's still, this kind of formulas are still much better than factorially growing sums that Feynman diagrams give by default. So let me actually get to the meat of the talk. So I want to start slowly by introducing the variables that we tend to use in amplitudes. So I want to talk about the spinning helicity formalism, just to define all these variables that allow me to write those formulas. And I want to dissect a very simple example of a 4-point component amplitude in QCD, and then sketch how the formulas that I just showed you can be derived. And then I also want to talk about how these methods can be also used beyond QCD for massive high spins. And then eventually, if one takes the classical limit, we could in principle even consider Kerr black holes as some, in an effective field theory kind of way, when a black hole is considered to be a point-like particle with some classical spin, which is just angular momentum of the black hole. Yeah, let's start. So massive spin helicity, I want to start with just again a 4-point amplitude, how just to remind you how you would derive it using a textbook method. Well, you would write two Feynman diagrams. Well, this is a color-ordered kind of amplitude, so I'm only writing 2 instead of 3. So here they are. I mean, they are written as very much in the textbook, maybe Peskin-Schroeder friendly notation. Well, of course, the labels here represent momenta, and I'm already trying to contract the notation. So the question is, are we done with just, is the shortest answer just the sum of these 2 amplitudes? Well, of course, you've already gathered that's not the case, but why is that the case? So, so the amplitude, the way the Feynman rules provide you a way to write this amplitude is in terms of momenta, polarization vectors, and external spinors for the massive quarks. But of course, you all know that in the amplitude, all of those Lorentz indices, so the vector indices for momenta, the vector indices for polarization vectors, and this implicit spinor indices for the external spinors of the quarks, they all have to be contracted. And the whole amplitude is not a function of those indices. They are all contracted. It's a scalar with respect to the Lorentz group. It's not a scalar with respect to the physical quantum numbers of the particles. So those are the helicities of the massless particles, and they are SU2 labels of the massive particles. So in this case, they're massive quarks, so just one SU2 label per quark. So they correspond to spins starting from 1/2 and so on. And in fact, so these labels, they don't correspond to the Lorentz group, they correspond to the little group of each individual momentum. So the whole setup boils down to the fact that as opposed to quantum fields that are transform under the Lorentz group SO13, we really care about in physics about quantum states, and they transform under the little groups, and the little groups for massless states are SO2s, and the little groups for massive states are SO3s, with the caveat that we want also to include half-integer spins, and then we go to the Lorentz group SL2C, and so the massive group, little group is SU2 instead of SO3. But that's something that we probably all will know pretty well. And but this this fact, well, this is just the general fact about what we should care about. But then, how do we make this work? And to make this work, we need to first start with the momentum, because the momentum is the primary quantum number of a particle that diagonalizes the translations. The translation part of the Poincare group, and the momentum. The first thing to do, if we want to include the spinorial representations, we need to map the momentum in R13 to a Hermitian 2x2 matrix, and then it becomes a bispinor. And that's just done by contracting it with 4 Pauli matrices, written explicitly here in this very standard representation. And then the scalar, which is the inner product with itself of the momentum, is the same as the determinant of this matrix. So then we have the and of course at this level, independent of the mass, we can represent very explicitly what the Lorentz group is on such a bispinor, and this is just the explicit action by the SL2C version of the Lorentz group. But now, since it's a bispinor, it acts on the left on the chiral index, and on the right, from the right on the anti-chiral index. But this is the same as just acting on the momentum with the usual Lorentz transformation. So this is the basics of spinor helicity, massive or massless. And then there's the usual dichotomy where either you have massless momenta and then the determinant is zero, and massive, then the determinant is not zero. And in the massless case, it's a very standard by now massless spinor helicity where determinant where a singular 2x2 matrix is just factorized into two spinors, massless helicity spinors. Then people usually introduce angle and square brackets, but this is just to track which spinor is chiral and which one is anti-chiral. So just since we're physicists, we don't like to necessarily write all the indices explicitly. So instead, we start to write brackets to track the chirality of the spinor. So this is the source of all those angle brackets in the MHV formula. In the for massless gluons, we just needed the left-hand side of this table. And on the right-hand side of this table, this is a slightly more recent version of the spinor helicity formalism, which is due to Arkani Hamid, Huang from 2017. And here you do something maybe slightly less obvious. So instead, since the determinant is not zero, well, you cannot factorize the matrix into two vectors or this spinors. But in fact, you can still factorize it into spinors if you realize that your little group is SU2. So in fact, you don't want to factorize it in terms of two vectors. You want to factorize it in terms of matrices. So you factorize one matrix as two other matrices. So what you've gained here is that you made explicit a new index, which is the little group index. It also is raised and lowered with the Levi-Civita, but now this Levi-Civita is not the SL2C bilinear form, but it's the SU2 bilinear form, which is of course a part of SL2C, but it's a part of SL2C in the same way as SO3 is a part of S13. So it's literally the like the spinorial version of the little group that is more familiar. So by doing this factorization of a bispinor into two spinors, but now with SU2 spin labels, you have, again, helicity spinors. They are now matrices. So, but you can still do this same kind of contractions. And now, again, you have a left-handed spinor and a right-handed spinor. And you again track the handedness of the spinor by the angle or the square of the bracket. So as soon as you drop these indices, as soon as you start writing spinor products without explicit SL2C indices, only the brackets track the handedness, the chirality of the spinors that comprise the spinor helicity expressions. And now they are also, these expressions start to depend on these little group indices, and this makes total sense because a massive particle can be quantized in different directions. So its spin can be quantized in different directions, and quantizing it corresponds to rotating in the rest frame of this particle. You can choose the quantization axis of the spin of a massive particle anywhere to be anything in its own rest frame, and so you have to have this freedom. It just makes total physical sense. So this is all of this was just a summary of the kind of the source of those expressions that involve left-handed and right-handed spinors. And once you have those spinors, well, those are just building blocks, right? So we've dissected our momentum, which is the most basic quantum number for a particle, into even more basic building blocks, which are left-handed and right-handed spinors. And now that you have them, you can use these building blocks to construct something more, well, other objects. So, a familiar object in massless gauge theory is a polarization vector for a photon or a gluon. And here you have the standard expressions for the plus and minus helicity polarization vectors. And here you have the momentum of the gluon, P, and at this level, you actually are forced to introduce some reference spinner, Q, which will not have any quantum number because it actually cancels, because the left-handedness is upstairs and downstairs. So there's no quantum number corresponding to Q in epsilon, but it still does depend on Q. And in some sense, you are forced to consider your massless vector particle to be a gauge field kind of particle. But in principle, at this level, you can just consider this to be using building blocks to construct something that you need from quantum field theory point of view. But in the same way, you can use the massive spinners, left-handed and right-handed, to comprise a Dirac spinner for an incoming electron, a quark, and or anti-quark, and you just you know, in the usual while representation, this is just stacking a left-handed and right-handed spinner together, and it follows from the properties of the two-dimensional spinners that the corresponding four-dimensional spinners will just obey the usual properties. So this is just a way to use these two-dimensional spinners as building blocks for the for quantum field theory objects. I'm not even doing purely on-shell things. I'm just slightly redefining usual quantum field theory objects in terms of slightly more basic objects, which are just while on-shell spinners. And then when you realize that this can be done, you also start seeing that everything is very neatly implemented in this way. For instance, the spinner, the Lula group transformations are just on the nose. They are just for massless momenta. You have spinners, left-handed and right-handed spinners transforming under the Lula group as just corresponding plus and minus phase shifts. And since they carry helicity half, you have the phase is divided by 2. And for massive, you naturally have an SU2 transformation that corresponds to the Lula group transformation or rotations in the rest frame of the momentum. But since the momentum, the whole construction is Lorentz invariant, you don't have to do the boost in the rest frame, do the transformation, and then go back. Everything's done just by everything's automatic from the spin helicity formulas. And so once you have these building blocks, then it's just a question of plugging in the definitions of those external wave functions into the usual textbook formula. And then you can say, oh, this is not better, right? Each diagram looks more horrible. But you know, at this point, it does, but at the same time, you know why it does. It only looks more horrible because this was a 4-spinner notation and this is a 2-spinner notation. So of course, at this point, I've only just plugged in the definitions. But then these definitions, they involve arbitrary reference spinners. And that's because we started with polarization vectors and they have gauge freedom inside them. And so one way to get to the right answer, to the short answer, is just to plug in a simple choice of reference spinners. So you can take the reference spinner of Q3 to correspond to momentum P4. So you just plug in spinners of Q3 as P4, and then actually one of the diagrams vanishes entirely. So the whole answer in this gauge is given by the first diagram. But spinner helicity can help without. So in principle, you could not plug in Q3 and Q4 as something specific. You could just massage this whole expression into this. It's also an exercise that a student can do. And in that case, both diagrams are not both diagrams are non-zero in general. But when you add them together, then they add to this, irrespective of what Q3 and Q4 are. But to know that, of course, you need to believe that the answer is simple. If you don't believe that the answer is simple, then you will just stare at these two Feynman diagrams. However, spin helicity helps regardless of the method. So far, I used Feynman diagrams from a textbook and just plugged in spin helicity as building blocks. But I could also start with something simpler, which is a 3-point amplitude. So again, at this point, I also just plugged in the definitions into the Feynman diagram. Now it's just one diagram, and then massaged it by using some identity. It's non-trivial at this point that the answer is independent of the reference spinner corresponding to the gluon, but this expression is entirely gauge invariant. It's hard to write it as gauge invariant, but it is. So you can just check that the dependence on Q vanishes. And then you can instead of doing Feynman diagrams for 4 points, you can go through the fully on-shell method of BCFW recursion due to Brita, Kachaza, Feng, and Witten, and proceed in the following way. So you take two spinners, 3 and 4, for instance, and you replace them by complex spinners shifted with a complex variable z. So now you're considering an amplitude which is a function of this variable z. So you've done a shift, a complex shift of your amplitude. And at the z equals 0, of course, you recover the answer. But you can also divide this amplitude by z and take a contour integral. And by the Cauchy theorem, you get the residue at 0, which is the physical amplitude, and a sum of poles that this amplitude may develop. And so in theories that we understand well, we can really make sure that there's no pole at infinity, or if we know that it exists, maybe we can even calculate it, but it's easier when it's 0. And if there's no pole at infinity, you know that a tree-level amplitude can only develop poles on the propagators. And so this amplitude that I've already computed through Feynman diagrams can be computed in a different way. It can be computed through the residue theorem so my amplitude is A of 0, and then the residue I can put on the left-hand side. And the residue that will depend on the z, the only propagator that will depend on the z will be the residue, will be this propagator in the 1,3 channel. And then the residue will put this propagator on shell. And once it's on shell, then I'm just gluing 3-point amplitudes. So this calculation just explicitly done here. And I get to the same answer, of course, because the method should give you the same answer if the answer is correct. But you see that I have not passed through any off-shell objects in this derivation at all, because all I did was actually derive an on-shell 4-point amplitude by gluing together two on-shell 3-point amplitudes. The main and then just shoved in a propagator in between, because that's how the residue theorem works, if you think about it slightly. So the main trick here, due to Brito-Kashazov, Feng, and Witten, is that these on-shell amplitudes are evaluated for complex momentum. So that's the non-trivial thing. So even though I'm computing an amplitude for real momenta at 4 points, when I glue the constituent 3-point amplitudes, they are evaluated. So these hats correspond to the complex momenta with some shift, and on this residue, this shift is not zero. The z is some specific value that is determined by cutting this propagator, and it's a complex momentum. The spinners of these shifted spinners start to correspond to complex momentum. So that's the main trick of BCFW, and it of course gives you the same answer. And we can use this trick to just bootstrap amplitudes in QCD to endpoints, and that's one way to derive the Park-Taylor formula. And this is a sketch of the derivation of the massive analog of the Park-Taylor formula that I presented earlier. So this one-term expression that contains all of the physical poles explicitly in the denominator, well, you can just bootstrap it from 3 points. So the first term is not this, but the first term is this amplitude, and then you can just bootstrap it by using BCFW and figure out. So here I shift I shift the spinners corresponding to glue n-1 and n, and the only propagators in this color-ordered amplitude come from a propagator like this and a propagator like that, and one of them actually ends up vanishing, and so the whole recursion always has one term. And when a recursion has one term, you always end up having one term in the answer as well, because your original 3-point amplitude, this guy here, is one term. You glue it with another term, you get again a 4-point, which is one term. You plug it in back into recursion, and you still get one term times one term. And so the whole recursion is very simple to solve, and that's the answer. So it's a very, very neat way to derive an infinite number of analytic answers. Well, when you don't have one term, sometimes, like in this case, there's 2 terms that don't vanish in the recursion, then the recursion will give you a linearly growing number of terms, which is still manageable, and you can just solve the recursion and derive an analytic expression. So in this paper with Achilleas Lazopoulos and Tsanxin Shi back in Zurich, we also applied this method for 4 quarks. So this is just to tell you that the case of identical flavors is easily obtainable from distinct flavors. So I can just consider the 2 pairs of quarks to be distinct. And I can start bootstrapping from this simple formula that I guess the easiest way to get it is still through Feynman diagrams, because it's a single Feynman diagram at this point. But then you can start adding gluons to this formula. And that's what we did with Achilleas and Tsanxin. And well, the answers are, of course, more complicated because the physics of the amplitude is more complicated. And so I can just flash one answer like this. I'm not even showing what this what these auxiliary spinners are, but and you can again, you can skeptically consider this answer to be too complicated to bother with it. But I would still argue that the sums here are still at this point linearly growing. If I'm not mistaken, yeah, I think this answer only contains a linearly growing kind of sum. So of course, each term in the sum also slightly grows, but it's nowhere near the factorial growth of an analytic expressions in terms of Feynman diagrams. And something else that I would like to point out, maybe more visible at this level, without all the gluons in place, is that an amplitude written in this way, well, it's for 4 quarks. Well, here it's only quarks, and each of them contains a spin label. So it's a 2 by 2 by 2 by 2 tensor in SU2. So in fact, this single formula, and each of these formulae for 4 quarks, they correspond to 16 amplitudes, 16 helicity amplitudes. So this formula contains quite a lot of physics in it. So the fact that it's not one term just means that physics is not trivial. There's some kind of physics in QCD after all, even when all the helicities are plus. So this is a neat expression for 16 helicity amplitudes. And mind you, all those quarks, in principle, the fact that this expression is covariant with respect to SU2 allows you to quantize the spin of each quark independently and arbitrarily. So it's just the question of which spinners you plug in. At the level of numerics, you are allowed to plug in spinners corresponding to this or another quantization axis. So it's a physical choice that you have to make when you compute a number from this formula. And this physics and this formula is covariant with respect to this choice. And it's covariant with respect to each choice for each particle, which is a feature of massive particles in the first place. So we have obtained results in this of this kind for also gluon insertions between like flavored quarks written here, but since the color order amplitude, the order matters. So we've also obtained expressions for distinctly flavored quarks with gluons inside of them. So and then we actually went and did something very pheno-like. We just decided to show how much better and having an analytic formula is with respect to just solving things numerically. And numerical methods are pretty good. The Behrens-Gille recursion, which basically uses Feynman diagrams, but in a recursive way, it's still a method of choice for many applications. And here we are showing basically the evaluation time on a laptop of these amplitudes going to 30 particles, and at least the amplitudes that we've solved, they grow in a tamer way than the evaluation time for the same amplitudes, but using Feynman diagram recursively. So that's it with the QCD. I'm happy to take questions on QCD at this point, or on anything whatsoever.
I had a question.
Go ahead, please.
I was hoping you could perhaps recap the description of massive particles in the spinor helicity notation.
Right.
It's
so
probably one of the more basic things, but it would really be helpful.
No. It's actually not as basic as you would think, right? Because the current version of the spinor helicity formalism that we now use is only 7 years old, right? It's quite funny that the step from left to right took 30 years. And so here the non-trivial thing happens when you take the momentum in terms of written as a bispinor and factorize it into two matrices. But now the index structure of these matrices is non-trivial, right? Because it's a matrix with an index alpha, which is SL2C, and another index which is SU2. And it really makes a huge difference because SL2C is the kind of index that gets contracted in an amplitude. It's a non-physical amplitude. It's a non-physical index from the point of view of the particle. Particle doesn't really care about your Lorentz indices. It really cares about its quantization axis, how you quantize its spin, right? It's the physical quantum number of the particle is its spin, and it's you quantize it along some axis. This axis is most easiest defined in its rest frame, and you're free to choose it to be anything, right? That's your usual quantum mechanics. And so this SU2 index, it corresponds to that physical notion of quantizing the particle's spin. Whereas this alpha index, that corresponds to your choice of coordinates in Minkowski space, and we don't care about it because it just gets contracted in the amplitude, right?
Right. So lambda basically becomes a matrix. I mean, it has a SU2
lambda
index
is a
and
matrix, yes. So here I wrote it as this lambda as as a matrix lambda a alpha. Here I write it still explicitly with indices, but now I've introduced this this bracket notation because then once alphas get contracted, you have you still need some way of representing what's left-handed and what's right-handed.
Okay, got it. Thanks.
Yeah. So, but the qualitative difference between the massless and massive is really just having this additional index, and again, it is a feature of massive particles. They do care about how you quantize their spin, because massless particles, they only have helicity. You cannot run faster than a photon, but you can run faster than an electron, and you can quantize its spin then in the rest frame in any way you want. But this simple step, it took the community quite a lot of time to really perfect and make work for us, not against us.
Thanks for that. Yeah.
Any more questions? So yeah, this we've gone through. Then once we make this work for us, we can actually start seeing some funny stuff. So I've so far have talked about this result, right? I've even sketched the derivation of it through BCFW. This is what I did in 2018, and this is so again n-2 gluons in QCD with two massive quarks. However, you can also, of course, consider QCD with two massive scalars. And that's what the kind of amplitude that Ferrari Rodrigo Talavera derived back in 2006. So you didn't need massive spin helicity for that because scalars don't need any quantum numbers to be represented here. And here's the answer. So I specifically wrote it in the same notation as the other answer. Right, so okay, very good. You can also go ahead and compute gauge theory that's spontaneously broken, and then you will have a massive. The first step is, of course, to do just massive spin 1, and then you can realize that the derivation can be generalized to higher spins. To any spin in gauge theory, a massive particle with any kind of spin, assuming something nice, assuming that the behavior under the BCFW shift is good, is as good as in QCD, you can derive this formula, and this formula you can see that it just interpolates and extrapolates the other two formulae. So this formula is just has a spin of the particle as a parameter, and it's true for s equals 0. It's true for s equals half. It's true for s equals 1 in the sense that you can indeed consider spontaneously broken gauge theory. Then it will start to contain some massive massive vector bosons that can be also gauged under the gauge group of the under the unbroken part of the gauge group, and but once you go beyond spin 1, that's not in gauge theory, that's considered to be higher spin. And at this point, you are getting some new results that you don't necessarily know what they mean, because you haven't written any Lagrangian, but still, it looks like the on-shell method gives you some amplitude that behaves really well. It behaves badly in the massless limit, but you see the pole in the mass here is only starting at s equals 3/2. And in fact, we know that in gauge theory, there are problems with higher spins, with spins larger than 1. And that at that level, this formula just tells you that, okay, don't take the massless limit. If you take the massless limit, that maybe you're outside the range of validity of your theory. So maybe your theory is an effective field theory. So the physics in this formula is not, I mean, the physics in the poles, that's correct. The physics in the massless limit also is suggestive of the behavior that we expect from high spins. And the physics of in the numerator here, well, it's the simplest possible way to represent the spin dependence on the two massive particles that you have here. Unfortunately, if you take other holistic configurations, not all plus gluons, then the same procedure slightly fails. But the fact that it doesn't fail in this sense, in this case, was already quite surprising. And it was even more surprising that in view of the fact that by the time we realized that this kind of dependence on the quantum numbers of the massive high spin particles could be related to Kerr black holes. So that was the original motivation to study these amplitudes really carefully, was because if you, I'm not specifying how you take this classical limit here, but let me just say that we know exactly how to take it by now very well. And the non-trivial thing that happens with these amplitudes, when you take this classical limit and you take it in a way that does not make the angular momentum of the particle vanish, so you take s to infinity in some sense. So as h bar goes to 0, you also take s to infinity, or it could also be formulated in a different way, even more rigorously. So the non-trivial fact is that what you get from these power kind of this, by the way, I didn't say, but this is a tensor product with full symmetrization in both little group indices. So this is a kind of just fully symmetrized spinor product. So it's a power, and this power dependence in the classical limit becomes an exponential dependence on the classical spin, and this exponential dependence is associated to black holes because the black holes were originally formulated, Kerr black holes were originally formulated using a Newman-Janus shift. And the shift in momentum space becomes an exponential of the momentum times the spin. So the shift in the spin direction in the coordinate space, originally written by Newman and by Kerr, Kerr used basically this Newman-Janus shift. In the amplitude language, it becomes this exponential. So this kind of spin dependence at the quantum level, it has something to do with black holes at the classical level. So that got us even more interested in this kind of amplitude, even though, again, as I'm saying, for other holistic configurations, things get more difficult.
Just a minor clarification.
Yeah, go ahead.
You said that Kerr used the Newman-Janus shift.
That's right.
In deriving his original metric.
I think so. Yeah, I think that's the history.
Okay. I thought Newman-Janus. It came after Kerr's paper, so, but I might
Really?
be wrong. I might be wrong. So
No, I think it was originally that was the tool that people started using, right, to produce new solutions for Einstein's equations. They just decided that, or they realized that there's a way to make things complex and then go back to the real slice, and it would still produce a new solution. At least, yeah, that's my impression from the literature. It's not like I've been reading these papers recently.
Yeah, no, of course not. Yeah.
Yeah, but of course, we usually in textbooks learn the Kerr solution in a different form, which is the Boyer-Lindquist coordinates. But I think the original way of writing the Kerr solution was almost reminiscent, almost explicitly using Newman-Janus shift.
Okay. Thanks.
Yeah, and so all of these suggest that, okay, maybe higher spins are complicated, maybe they correspond to an infinite number of effective field theories for composite particles, but maybe in this space of EFTs for higher spins, there are still some kind of simple EFTs, and the simplicity might even be related to Kerr. So maybe black holes have something to do with such high spin particles that are simpler than your garden variety high spin particle, right? Your nucleus with spin larger than 2 or 1. So okay, very good. So that's so we took it seriously, and let me remind you what happens. Okay, I'm running out of time a little bit, so let me be quicker here. So let me remind you what people tended to use for massive high spins. So the standard choice in literature, starting from Fierce and Pauli, was taking symmetric traceless tensors with S indices, specializing to integer spins for a moment. And that choice in the spinor language, it corresponds to taking a field that has S chiral and S anti-chiral indices. So this is fine. This is irreducible representation of the Lorentz group. However, it's really badly reducible with respect to the little group. So this representation can be called SS because it has the same number of chiral and anti-chiral spinorial indices, but it's really bad with respect to the little group, or in other words, there is just too many degrees of freedom in each such tensor. And that is actually true also for a vector, right? So even for spin 1, you already know that there's 4 degrees of freedom here, and you only need 3, 2s plus 1. This is the number of physical degrees of freedom that you want in a massive particle. So even spin 1 actually contains a superfluous degree of freedom. But okay, spin 1 is a special case. It's slightly easier than higher spins. But this is a generic problem, right? In field theory, as soon as you go beyond small spins like 0 and half, you have this problem. You just have to you have to remove the degrees of freedom. And one way to remove them is to impose the standard way to remove them is to impose transversality. But that's hard, and people have been using like a whole bunch of auxiliary fields, starting from Fierz and Pauli and Singing-Hagen in the 70s, and more recently even a larger amount of such fields by Zinoviev. And this is all well and good. I mean, you can do it. Zinoviev's method is very good. Is more powerful when you try to introduce health interactions. That was a huge problem before Zinoviev. And we have actually used this method with my collaborators, having learned it from Zhenya Skvortsov. But my talk is not about this method. My talk is about doing something simpler. And so what we decided to do by looking at those amplitudes with Zhenya was also just completely change the approach and switch from this field that has S chiral and S anti-chiral indices to a completely chiral field. So a chiral field with 2s chiral indices. So, okay, what can you write for such a field? Well, the first thing you can write is the free Lagrangian. And the free Lagrangian can be written almost, so this is basically a scale Lagrangian where it looks like a scale Lagrangian. The only difference that makes it non-scalar is the fact that these indices are not some flavor SL2C group, but this is the spacetime SL2C group. So that's non-trivial. And once you impose that these indices transform in the same group as the derivatives, then of course you have to quantize this field using building objects that mix those indices. And those building objects are the massive spinor helicity, the massive helicity spinors. So here they are. So this is how you quantize this field. This is just basically using textbook methods. The only equation of motion that you have to impose is the Klein-Fock-Gordon equation, plus the fact that yes, those indices are those indices are not just flavor indices; they are SL2C. They are Lorentz indices. So you have to introduce these objects as a polarization vector, well, not vectors, but polarization spin tensors. So you can write the Feynman rules. Well, at this point, it's just free field theory, so your Feynman rules are a bit trivial. But okay, a propagator is a unit, is a scalar propagator times a unit operator in the space of fully symmetrized 2s SL2C indices. So this is a unit operator in the space, and your external wave functions are these constructed from the helicity spinors. And then you can also introduce interactions without any trouble, without the old standing problem of unphysical degrees of freedom. So the most basic way is just to introduce by making derivatives covariant with respect to some gauge field. And yeah, it does work. It just produces some amplitudes, and it exactly produces in the chiral sector, and even in the anti-chiral sector, it produces this dependence on the spin degrees of freedom. So we've slightly overshot our way, because now we only wanted such amplitudes for all pluses, but actually this whole theory, I can just write the full tree-level S matrix for this theory. I've introduced these gauge interaction in such a way that actually the whole theory is basically scalar field theory with the gauge field times prefactors that are just chiral spinor products tensored and symmetrized in the most basic way that there is, at least for this kind of objects. So we actually have this. This is one example of a complete theory for which we know the complete S matrix, and it's a bit funny that you can just calculate it in this way. Of course, it's extremely chiral. This theory is constructed using chiral fields, and its amplitudes, they behave very chirally because I have this chiral spinor product for pluses, but I also have the same chiral product for minuses. And this is not normal. Like normally, if we have chiral spinor product for pluses, then for minuses in helicities, we would get anti-chiral spinor products. So both the formulation of the theory and the actual physical content of this theory are chiral. But of course, yeah, and you can make it less chiral. This is, or you can also, of course, do SO2, which is QED, or you can introduce gravitational interactions, and it will again be chiral. So we're using chiral fields, so we get in a chiral theory by default. So this is quite unsurprising, but it's not that if you have a chiral formulation doesn't mean that the theory itself must be chiral. Of course, you can reformulate a non-chiral theory in a chiral way. And in fact, and that just means that parity is in a chiral setting, parity is no longer trivial, so you have to do some work. So you need to add more interactions. This is a typo, but this is also natural in effective field theory. You should actually be adding all those interactions with free coefficients and maybe fixing those coefficients from some other physical principles or experimental or other data by using EFT matching. So it's not unnatural to introduce more interactions in this picture. And in fact, this is an explicit Lagrangian from which you can derive now non-chiral amplitudes for that were first written in the on-shell fashion by Cunningham and Huang. And those are the amplitudes that correspond to curved black holes in the classical limit. So they are non-chiral because for plus you have chiral and spinor product, and for minus you have antichiral. So at three points we have restored chirality, restored parity by adding this additional interaction with the self-dual field strength of the gauge field. And then you can start using this for black holes, and I think I'm entirely out of time. So let me just say that there's been a long-standing debate about what the 4-point amplitude for rotating black holes should be at the classical level, but also at the quantum level. So we now that we discovered this way for writing Lagrangians for massive high spin particles, we had some new info, some new insights into writing amplitudes and then taking the classical limit. So even before the classical limit, we wrote this amplitude, and then after taking the classical limit, it's written here in some other variables that are now connect better to the variables relevant for classical physics. And these answers that we obtained, they are they are the best answer yet for black holes. This is not a derivation, because of course the fact that black holes and massive high spin particles have anything in common, it's still a conjecture. It's only we only understand it at 3 points, and going to 4 points is non-trivial. But we have a proposal that meshes well with the Tucholsky equation solutions just from pure GR done by these authors. And also it's compatible with other amplitude results that other people were writing from not using massive high spin theory, but they were starting from something classical and just thinking about what you can write. So I think they have confirmed that our answer, so their answer is basically our answer with something set to 0. I think with W set to 0 or Z. Now I'm a bit confused, but basically we have even more information than they have. So now there's still some debate about what that amplitude is, but that's a new result, and that was obtained in a very roundabout way from massive high spin theory with a gravitational interaction. So to sum up this talk, I'd like to just remind you that most of what I've done was relying just on the fact that relying on the SU2 covariance corresponding to the arbitrary spin projections of massive particles, something extremely physical. And since 2017, we know how to write covariant formulas for on-shell amplitudes and make this work for us. And that allows us to write elegant form for 2-quark amplitudes with endpoint at arbitrary multiplicity. That's a very QCD application, done also with QCD person, Achilles. But then, not being purely QCD people, we also applied it to massive particles with spin and in the classical limit with black holes. And in the process, we discovered a new chiral field approach to massive high spins, which solves the long-standing problem of unphysical degrees of freedom. It introduces the problem of parity, which is no longer automatic, but that is, I would argue that is a simpler problem. And using these new methods, we obtain new results for quantum high spins and in the classical limit for rotating black holes. And those are the most recent results. Just published in a PRL in August, 2 months ago. So thanks a lot for your attention. Yeah, I'm happy to take more questions.
Okay, thank you for your interesting talk. Questions, please. This is a little bit not typical subject for our seminar, but in any case, I hope that some people
I have a short question.
and will ask you questions.
I have a very naive question, Alexander. So I don't quite understand exactly the relation between the higher spin amplitudes and black holes. Is it analogous relation or it is exact relation, something we can really test something about black holes with observations?
Well, observations of black holes, that is LIGO's job, basically, right?
Yeah.
So we are interested in the binary dynamics of black holes in GR to start with. So this is a purely classical problem. And we would like to contribute to solving it analytically, perturbatively in the post-Minkowskian regime by using amplitude methods. And one way to go about it is to start from a quantum field theory and then take the classical limit usually as early as possible. But when it comes to rotating black holes, it turns out that not that much known, not that much is known even at the classical level. So yeah, so we at 3 points we know exactly what we're talking about by now. So we were figuring this out since 2018, and now it's sort of a solved problem. However, it's only 3 points. So at 3 points, all you need to do really to make this connection that I outlined here is to take a linearized black hole solution, so linearized Kerr solution, and then well, plug it into an amplitude calculation in the most naive way. And there's no multiple ways to do it because this is leading order. You can basically do the simplest thing possible. Just basically do a Fourier transform of the stress energy tensor, and it will contain an exponential. The spin dependence will exponentiate.
So it will come from the linearized
Kerr.
Kerr
Yeah,
form.
exactly. So
Okay.
it's slightly obscured by the fact that this exponential is, well, it's like in the complex direction, but with the length of the spin. So there usually stuff like this is written in terms of Cauchys and Cinches, so hyperbolic functions. But if you massage it, you'll just see an exponential, right? Because those are the physical thing.
Excuse me, can I say that in some sense that is similar to a canal approximation or not?
Well, this exponential is not about the econal approximation. No, yeah, this is important. The econal approximation is important in the classical limit. It's indeed the relevant approximation for small angle scattering. But this exponential is a different exponential. This exponential is really about the shift, right? The shift, by saying shift, I mean the translation. So the shift, the point of the Newman-Janet shift is if you take the Schwarzschild solution and in some sense translate the center into the complex direction, then you will get Kerr. That's how Kerr was basically constructed in the first place. And that shift, and of course, translation is generated by derivatives. Derivatives become momentum, and they exponentiate because we are talking about the finite shift, not so yeah, they're generated, so you have to exponentiate the generator. So the exponential dependence on the derivative and at the same time on the momentum, on the angular momentum of the black hole, that's just almost inherently in the Kerr solution, right? It's just you can see it by looking at the linearized Kerr. Even if you don't want to look at the full Kerr, you can just look at the linearized Kerr and you will see an exponential structure. And so this exponential is about the shift. And the non-trivial thing here is that there's some kind of a hidden exponential in this tensor power, symmetrized tensor power of a spinor product. So of course, the tensor power is not an exponential by itself, but if you take s to infinity, some factorials will start combining with themselves in such a way that instead of combination, instead of binomial coefficients, you will end up having just 1 over n factorial, and you will get an exponential. So those are, of course, written in very different ways, but if you have questions about it, I'm happy to discuss, but it definitely wasn't something that I was trying to explain carefully here. It's just in this arrow, right? Very schematically. So I don't know if I should go on in more details about this. I can go on as it's one of my favorite topics, so I can go on for hours about this.
Okay, thank you.
Yeah.
More questions, please?
Yeah, I just wanted to clarify that Kerr's work actually preceded the Newman-Janus work. So I haven't looked at the Kerr paper itself, but I don't think that they used the Newman-Janus. He didn't use the Newman-Janus algorithm.
Yeah, okay.
I might be wrong. So
I need to double check that.
yeah.
But anyway, yeah.
It's just a historical note, but still.
Wait. So Kerr, okay, actually now I remember. So Kerr's solution was originally written in the Kerr-Schild coordinates, not Boyle-Lindquist. So Kerr-Schild, I think Kerr-Schild coordinates are still slightly more obviously related to the Newman-Janus shift. Well, yeah. Maybe I should go back to the old literature and double check what came first. But let me still say that I guess it's still a defining feature of the Kerr solution. This Newman-Janus shift property.
Yeah, no, of course. It's Newman-Janus is also something that is used in the double copy, if I'm not mistaken.
Yeah, well, in the double copy where you want to get Kerr from some kind of square root Kerr, yes, of course.
Yes,
yeah.
Yes.
That's a defining feature. So if you want to double copy by preserving your understanding of what's going on, you have to put it in. Yeah. Yeah, the double copy is a more general statement, of course. It has nothing to do with Newman-Janus shift.
Okay, more questions? Because the subject is a little bit not typical for our seminar, so I don't expect that too many people would like to ask you questions. But
well,
okay.
I hope, yeah, I'm still open to questions.
Okay, please, yes, please ask the question. Also, you can ask some general questions, yes.
I can ask more questions if there are no other volunteers. Is that all right, Irina?
Are you an expert in the subject? Maybe better.
Me? I don't know. I don't know, Irina. That is for other people to judge. But you can have a look at my archive listing and decide. I mean, I just think it's very remarkable that the scattering of elementary particles and the scattering of black holes should have any relationship at all. I think that is really extraordinary.
Yeah, it is remarkable. And in fact, well, the earliest kind of paper that talks about it that I know is from 91, I think. So people have been thinking along these lines for a while now. Let me try to
No,
remember.
I know that several people have looked at this notion that the Kerr geometry corresponds to an elementary particle, right? I mean, including
Yes.
Nima, I think, in one of his papers.
That's right. Yeah.
Yeah,
So-
but still, you think of general relativity and you think of Kerr as something
Yeah. Well,
happening at
Nima's
large
paper,
scales. You know.
Nima's paper is simultaneous with this paper of mine. So we were in touch
okay.
with Donald
Okay.
O'Connell when we
My
were
my
writing.
apologies. I am just
That's okay.
becoming
Yeah,
aware
yeah.
of your work. So yes.
No, that's okay. So yeah, Nima's paper is exactly about this this transition, and yeah, we first saw this transition in a slightly different way in 2018. Then 2019, we sort of had a even better version of this. So now we really, yeah. So that's the paper that you were talking about. I think okay, Hamed, Huang, and O'Connell. Yeah.
Sasha, may I ask you some general question?
Go ahead, please.
Yes, my question is like this. If I will consider somewhat different, for example, not GR solutions, but for example, Schwarzschild de Sitter, black holes or whatever, is there a chance this will start corresponding to something? For example, to scattering in de Sitter or anti-de Sitter space?
Well, you want to introduce a non-trivial background.
Well, not really very much non-trivial. Let's say a cosmological constant, okay? Positive or negative is the other question. If I add lambda, I can construct easily a Schwarzschild de Sitter solution. Yes, it's easy to construct. Can this have chance to correspond to something?
Sure. Yeah, it will correspond to something. It's just, I guess the question is, do you have tools ready for what it corresponds to? So here we're talking about flat space, so there are tools on that different sides of the problem, so that we are playing with that, and that's what makes us happy.
Well,
What
in
you're talking
principle,
about, I'm less familiar with how well. We know people who compute amplitudes in de Sitter and anti-de Sitter, right?
yeah.
So the state of the art for amplitude methods in those spaces is well, less advanced than in flat space for a good
Yes,
reason.
sure. But for example, in inflation, which is a de Sitter, yeah, and people try to compute a lot, and I'm now became curious whether this may have correspondence with amplitudes which people compute on de Sitter, and try. So it should. So you understand, as you how they present it, it looks like if I now start consider Schwarzschild de Sitter, it will give me something about amplitudes during inflation, hypothetically. If I'm powerful enough.
I mean, so the name of the game is, of course, going the other way. So we're trying to use amplitudes to compute GR, right? It's not that we want to compute GR and then think about the amplitudes. GR is hard already. Just
Okay.
So GR, people solve it numerically using numerical relativity, but perturbative calculations in classical GR are extremely hard, and a lot of complications in those calculations come from general covariance, from gauge symmetry. They have to fix the gauge symmetry, and they introduce a lot of rubbish into well, it's rubbish from our point of view because, of course, amplitudes are gauge invariant, so we never care about the rubbish. We just compute physical objects, and we fix some frames only at the very end when you want to decide, when you want to plug numbers, then you decide, okay, how do I quantize my spin? Well, maybe in this way. Okay, but you only decided at the point where you plug in experimental data, right? You want to really correspond to some experiment, but your amplitude should be covariant with respect to any kind of choice that you would have. And in the same way, and this is not the case for a classical calculation that doesn't do amplitudes, right? It passes through equations of motion that are unsolvable unless you fix the gauge. So you fix the gauge, and then you're tied to this gauge, and then somebody else uses another gauge, and you cannot even compare your answers in many cases, right? Because many answers are partial, like somebody computes something, some part of the answer, and in order to compute the other part of the answer, you have to still use the same gauge. And if somebody else computes a similar part of the answer in another gauge, then these answers may have nothing to do with each other, right? So it's a huge problem in classical calculations that people that go into high orders in GR, they basically have their favorite gauges and they don't talk to each other. Well, they cannot compare results unless they compare some final numbers. But at that point, they can also just be talking to experimentalists. So whereas we deal with gauge invariant objects, and we're trying to leverage that in order to help GR. So that's why what you were saying is the opposite, right, of what we are trying to achieve. We are trying to go from what we know amplitude and proceed to GR that we'll know less well how to do in the GR way, but we know how to encode all of the physical information about GR into amplitudes. Because those amplitudes, they actually recurse in the same way as QCD.
Okay, I understand. Yeah. I understand. Thank you.
Okay, more questions, please? May I ask also some technical questions?
Yes,
so, for example, from string theory, also from gauge theory, we know that amplitude for gravity and sometimes can be factorized as a product of two amplitudes for gauge theory. Do you expect that your calculation is useful to do some calculation in gravity?
But yeah, I've been talking about gravity for the second half of my talk. And well, yeah, I guess the first half of my talk was QCD, and the transition was almost, I guess I didn't even point out the transition. But the transition, one part in the transition happened here. So let me write this. So here's some formula in gauge theory coupled to two massive high spins, right? This is this formula. And then there's another formula here in gravity now. So you see there's the Riemann, the Ricci scalar here. So, and then the covariant derivatives now have the spin connection, the anti-self dual spin connection for that matter. So at this point, I'm talking about gravity, and the amplitudes factorize in the same way. Of course, the scalar amplitude is different. This is the scalar, this is the amplitude for a massive scalar coupled to n plus helicity gravitons, whereas this one is the color-ordered amplitude for a massive scalar gauged with n minus 2 gluons. So but you can see that the formula is the same, and these formulas, these O plus formulas, they can be obtained one from the other by using the double copy, exactly the same kind of double copy that you're talking about, the one that was originally derived from the correspondence between the closed and open strings, and then in the field theory limit, it boils down to gauge theory squared equals gravity. So I didn't focus on the double copy part of this, but of course there is a double copy story. It's limited. I would say it's not as rich as it could be because of the EFT nature of the massive part of this problem. But in the non-EFT part, let's in the part where you see this amplitude is just minimal coupled scalar, that double copy works perfectly, just out of the box. So yeah, it's we do tend to jump between gauge theory and gravity all the time in our field, indeed, and we almost take it for granted. So we don't. I forgot to focus on that step, even at all.
Okay, thank you.
Yeah, thanks.
More questions? If there is no more questions, let's thank the speaker again. It is not so simple to present the talk with so many formulas.
Yeah, thanks.
I think you
Yeah.
succeeded.
Thank you very much.
Thank you. Thank you. Bye-bye.
Bye. Thanks.
Bye-bye. Alexei, I have one more questions for you. One more question. By the way, yesterday, Lyudmila Starobinskaya called me, and she is very interested to get a video, not video, maybe some kind of recording of a seminar dedicated to Alexei Starobinsky. What we can do for her?
Well, I can do something, simply send her link or whatever.
Okay,
but she
okay.
can download. Okay, I will do something, but not immediately. Can you ask her to wait for, I don't know, 1 week?
Yes,
maybe?
of course. But the problem, I understand that she cannot use the computer because her eyes is not work at all.
Well, up to this stage, I cannot really help. I can help with a link, with some uploading to some alternative site, but not using computer is a bit more tough problem. Yeah.
Okay, maybe I don't know. Okay, in any case, I will write her that you are ready to give a link.
Yes,
And
of course.
she can find somebody who will help her.
Yes, I can upload it to something alternative to YouTube so that she can take it
Okay.
easier, but then someone maybe should really assist her personally.
And the same concern, of course, but we will discuss maybe separately about all other talk.
Yeah, this will do.
Okay, thank
Okay,
you.
good.
Okay,
Thanks a lot.
Bye-bye.
See you.
Bye-bye. See you.
Bye.
Bye bye.
Bye-bye.